So far, the only way of testing whether a series is convergent or not is to apply on a case by case basis some of the simpler theorems that we have proved, like Cauchy's convergence criteria or monotone convergence theorem or Cauchy condensation test. Now I'm going to give a broad class of tests that are usually sufficient to deal with many different types of series that arise in practical use. So the heart of all these is the comparison test. Theorem, comparison test. Comparison test. Let 0 less than or equal to an less than or equal to bn. Okay. Then first part, if summation bn converges, then so does summation an. Part 2, if summation an diverges, then so does summation bn. Okay, the proof of part 2 is fairly easy, so I will just prove part 1. Suppose summation bn converges, then by the Cauchy convergence criterion, we have for each epsilon greater than 0 n epsilon in n, such that if n is greater than or equal to m is greater than n epsilon, then summation modulus of bj as j runs from m to n, this is less than epsilon. Okay, sorry, I made a mistake. The summation should be inside the modulus. So modulus summation j equals m to n, bj is less than epsilon. Okay, but these bj's are all positive quantities. That's our assumption. So what we get is bm plus dot 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 bn is less than epsilon. Okay, in other words, am plus dot 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 an is also less than epsilon because this is less than or equal to this. That's our hypothesis. 0 less than or equal to an less than or equal to bn. Okay, so by Cauchy convergence criteria, again remember the Cauchy convergence criterion is an if and only if condition. If a series is convergent, then this must happen. If this happens, then the series is convergent. So by Cauchy convergence criterion, we are done. So we have proved the comparison test that allows us to prove that a series converges by comparing it with some other convergent series. Note that to apply the comparison test, you must have a toolkit of several convergent series at your disposal to compare with. You will develop that toolkit in the next few modules and in the exercises, of course. So it's always good to know some collection of nice series which converges and use it in the comparison test. Let me illustrate by proving another popular test for convergence. This is called the ratio test. Let's prove this ratio test. Suppose an is a sequence and assume that limit n going to infinity a n plus 1 by an exists and is equal to L. Okay. Then number 1, if L is strictly less than 1, then summation an converges. 2, if L is greater than 1, then summation an diverges. Number 3, if L is equal to 1, then this test is inconclusive. Suppose you take the limit of the successive ratio of absolute values of the sequence. In particular, the denominator should be non-zero, otherwise it doesn't make sense. I'll make some remarks regarding this after we conclude the proof. Suppose the limit exists and is equal to L. If L is strictly less than 1, then summation an converges. If L is greater than 1, then summation an diverges. If L is equal to 1, then this test is inconclusive. It doesn't give you any data. Let's deal with part 3 first. Well, part 3 is proved by exhibiting examples, right? That's the only way you can prove part 3. That means you have to exhibit examples such that in one case the limit is 1 but the series converges, in the other case limit is 1 but the series diverges. By exhibiting examples, take 1 by n and 1 by n squared, and I leave the details to you, which is which. Okay. Now, suppose L is strictly less than 1. Then we can find R less than 1 such that L is less than R is less than 1. You will understand in a moment why I have chosen this R this way and why I have used the notation R. Okay. Now observe that as limit mod an plus 1 by an converges to L for some fixed n and small n greater than or equal to capital N, we have mod an plus 1 by an is less than small r. Justify this. What we have done is the following. We know that the sequence mod an plus 1 by an converges to this capital L, and we know that this capital L is less than 1. What we are doing is we are squeezing in this r in between L and 1. By the epsilon n definition of convergence, for suitably large n, the ratio must be very close to L. In particular, the ratio must be strictly less than R whenever n is greater than or equal to this capital N. Okay. Now, how does this help us? Well, this shows that mod an plus 1 is less than R times mod an, right, in particular. Similarly, an plus 2 is less than R times mod an plus 1 is less than R squared times mod an plus 2. Okay. So, what will essentially happen is, if we consider the series summation j equals 1 to infinity mod a n plus j. If I consider this new series, then I know that 0 is less than or equal to, call this new series, let's say bj. 0 is, now let me not call this bj, let me call this Cj. 0 is less than or equal to Cj, and Cj is strictly less than r per j mod an. As you can imagine, we are now going to use the fact that the geometric series converges. Fine. So, how does this help? But r is less than 1, call this bj. R is less than 1, so summation bj converges. Summation bj converges. Therefore, summation cj converges. This follows immediately from the comparison test. How does this help us? Well, observe that our original goal was to show that summation an converges. Summation an converges. Now what we have is summation mod an plus j converges. This is what we have. But these both are intimately related to each other in the following way. By Cauchy convergence criterion, for n comma m suitably large, we have summation j equals n to m or m to n, and n is greater than m, mod a n plus j is less than epsilon. So I must say fix epsilon greater than 0. This is simply because summation mod a n plus j converges. Okay, but modulus of summation aj, j running from m to n, is less than or equal to not j running from m to n, j running from n plus m to n plus n is simply less than or equal to summation j equals m to n mod a n plus j, which is in turn less than epsilon. Okay, hence the series summation an also satisfies the Cauchy convergence criteria. Hence summation an is convergent. So this proof was a bit involved, but all I have done is apply the comparison test at this particular point. That's the only non-trivial step in this whole proof. The rest of that is all just simple basic manipulation. To somehow apply the comparison test, I have compared a different series, not the original series summation aj, but a different series to the geometric series rj mod an, which converges. Okay, and by the comparison test we know that cj converges, and from this series summation cj converging, we have concluded that the series summation an converges. Okay, now one portion of the proof that just involved an application of triangle inequality is a useful proposition. It's a useful proposition. I am not going to prove this because we have already done it as part of the proof of the previous theorem. Suppose summation mod an converges, then so does summation an. We have done the proof of this as a part of the proof of the previous theorem. So this prompts the following definition. A series summation an is said to be absolutely convergent if summation mod an converges. If summation an converges but summation mod an diverges, then we say summation an is conditionally convergent. Conditionally convergent. Note very carefully that the root test, because there are absolute values involved, this root test is actually a test for absolute convergence and not conditional convergence. If you are going to conclude that a series converges using the root test, you would in fact be proving something stronger. You would be proving that the series is absolutely convergent. Now, one more remark I want to make regarding the proof of the ratio test that we had done. The proof of the ratio test we had done at one step involved creating this new series, which is essentially just the latter portion of the original series with an absolute value. Essentially, we call that the tail of the new series. Okay, so what we are essentially doing is we are ignoring the first few terms and just starting a new series from some particular point of a given series. Okay, now it must be 100% obvious to you that whether a series converges or not does not depend on the behavior of the first 10, 100, 1000 or 100,000 terms. It depends only on the behavior of the sequence beyond something. And this is amplified in the Cauchy convergence criterion, where all you are required to show is that summation j equals m to n aj is less than epsilon for suitably large m and m. Therefore, modifying the first few terms of a series is not really going to affect its convergence behavior, and we have sort of seen this more rigorously when I proved this in detail by considering the sequence summation cj and comparing it with the original series, right? So keep in mind that all the convergence tests that I am stating can be modified to take into account these remarks, that the behavior of a series really depends only on its behavior of the tail. So for instance, in the statement of the comparison test, I am saying that you require 0 less than or equal to an less than or equal to bn. By a similar proof to what we have done for ratio test, you can show that you don't really need 0 less than or equal to an is less than or equal to bn. You just require this inequality whenever n is suitably large. You don't require it for all values of n. You can modify the proof to see for yourself that what I'm saying is true. Okay, excellent. So we have now defined absolute convergence and conditional convergence. In the next module, we will see a test for detecting conditional but not absolute convergence and give several examples. This is a course on real analysis, and you have just watched the module on tests for convergence.